So again, in a problem like this, our interest isn't really in the electric field. Our interest is in the amount of enclosed charge. Now, how about D? That would also be zero flux. The only one here that has any actual flux would be B, right? So I look at B, it clearly has an enclosed charge of 6Q. Therefore, there are electric field lines that exit B and don't terminate in B. But the amount of flux that enters C and exits C is the same. Same for the amount of flux that exits and enters A is the same. Does that make sense? You should be able to describe it in that way. It's about the total amount of flux that may enter or exit a region of space. I'm not upgrading to go beyond the advanced plan. Advanced should be good enough. And that was already like $60 for the year. So, all right. So we get this idea about simple questions like this and how they're related to Gauss's law. I don't want to belabor it too much. You can probably imagine that this probably looks like a multiple choice question. You guys kind of see that? So, I mean, on your test, there will be something that looks like this. There is another use for this, but we need to wait till we have electric potential, but it's still no more difficult than what we're talking about here. Okay? So let's go ahead and go on to the in space. We'll say it's an infinite sheet, but I can't draw an infinite sheet. All right, got it? So this is just a plane in space. Now, to describe the sheet, we can either say that it has a charge density of sigma, which would be total charge divided by the total area of the sheet. Now, in the future, this might be like a plate for a capacitor, which we might treat as a sheet of charge, but note that it probably has a specific area, even though it's not. We're treating it like an infinite sheet. So we might say it's like Q over S squared or something like that for like a squared sheet. But we would be saying that we're very close to it, very close to its center. So we could treat it like it's infinite, even though it's not. Now, to use Gauss's law, I need to do a couple things as a reminder. First, Gauss's law requires that we calculate flux. It also requires that we create a Gaussian surface. Now, I'm trying to emphasize this part a lot. And by emphasize, you really try to give you some simple little things to think about. We are creating the Gaussian surface. The surface is a construct. It's not a real surface. It's something we construct for the purpose of using it in Gauss's law. So when I say what Gaussian surface would we use, this is something that you create that has hopefully symmetry, but more importantly, has clear, distinct surfaces that you can use for the purpose of integration. So we saw for the point charge, the sphere worked great. We saw for the infinite line, a cylinder works great. For the infinite sheet of charge, our goal is to consider what the electric field would be near its surface. So if I just slide this off to the side for just a minute, an infinite sheet would just look like a line if we were kind of lined up with it, wouldn't it? And so we're talking about maybe a point, a distance z away from its surface. Is that okay? Can we come up with an idea of what we think the electric field might look like before we deal with our Gaussian surface? This is our step 0. It's trying to get an idea of what we think the electric field is likely to look like near the surface or near the shape of the object. So, not crazy in thinking that the electric field is probably going to be somewhat symmetrical and uniform coming away from the sheet, like so. Can we all kind of get behind that? And both sides of the sheet, both top and bottom, would experience the same kind of uniformity of the field lines. That all seem okay? So when I'm thinking about what kind of surface I'd like to use, I will probably need a surface that protrudes both on the top of the sheet and the bottom of the sheet. Would you guys agree with that? So I'm thinking perhaps another cylinder. Something like so. So, I'm looking back at this surface here, something that is got a portion that is above the surface, and then a portion that is below the surface. That's the best I can do with my artwork. Is that okay? You guys can kind of get an idea for that. Is that all okay? All right. Just in kind of evaluating it, I want to make sure I take my can, my cylinder, and center it so that I have equal amounts of or equal distant on top and bottom, so that this is also Z. Does that make sense? So that I'm trying to exploit that symmetry a little bit and make sure that I have kind of a symmetrical shape here. And I don't know, we can make the top, say the top has radius R so that it has an area of pi R squared for the top, and maybe an area then of pi R squared for the bottom. Does that all make sense to you guys? All right. That would mean the area for the side would be 2 pi R times 2Z. Does that make sense as well? Where 2Z would be the height of the can. All right, so I'm just kind of setting up some geometry ahead of time so that I don't have to worry about it too much later on. With the can, I see 3 distinct areas: the top of the can and the bottom of the can and the sides of the can. Do you guys all agree? I believe there's only flux through the top and bottom. I think if we line the can up perfectly, there'll be no flux passing through the side of the can. Does that all make sense to you? Remember, we're trying to exploit the symmetry here, so we're trying to choose a surface that will make doing our integration easy. So all these things we're talking about are evaluations of the surface itself compared to the electric field. So step 0 was, what's the electric field shape? Step 2, choose a Gaussian surface that will exploit the symmetry of your electric field. Now, step 3 is going to be to start assembling our flux. So I'm going to start by assembling the flux. And the first thing I'm going to notice is that I can take the total flux and break it up into the flux that passes through the top plus the flux that passes through the bottom plus the flux that passes through the sides. That all work for everybody? And we've already kind of had a verbal argument that the sides is going to go to 0. Now, for those of you who are just clinging on to this, the electric field is in that direction. Near the sides, the area would be this way. So do we see that the cosine is going to be 0 there? And that's why there's no flux. But at the top, the electric field is going to be this way, and the area is going to be this way. So I think that'd be the cosine of 0 for my dot product. That all good for you guys? And at the bottom, the electric field will be that way, and the area will be that way. I'd say that the cosine will be 0 there as well. That all good? All right. Just making sure we have no cosine 180s or anything weird like that. Trying to make sure we're not playing fast and loose with the rules. We're not making it just a verbal argument. We are making a mathematical presumption based on how we set up our Gaussian surface. But that also means I can come back over here and realize that this will just be E times dA for the top, and this will be E times dA for the bottom. I can remove the dot product and not worry at all about the vector portions. We've handled the vector portions for all 3. I spend a lot of time saying those kinds of words. it's now when you might want to write a few things in your notes, because your homework is going to have some examples where maybe you can't just get rid of the dot product so easily, just to make sure that you are thinking about it. So remember, the dot product is a relationship between the direction of the electric field and the direction of your area. And the area has to be perpendicular to that surface. It's a normal to the surface and faces away from the interior. Now, I think this part is got some obviousness to it, but again, I'm trying to be patient and deliberate. I tried to line up my can, my cylinder, so that the top and bottom were both the same distance from the sheet. Does that make sense? I think the electric field is going to be uniform enough where it will be the same value everywhere on top of the can. Does that seem okay? And because I made it the same distance on the bottom, can we say that the electric field is the same value everywhere on the bottom of the can, and that top and bottom electric field is the same, at least at the surface of the can? So that means for both of these integrals, I can take the electric field out. Our goal is to try and do that whenever we can. And this suggests that my total flux will now be based on just whatever that area is going to be. Now, not much to do here. The area at the top of the can we already worked out. It's pi r squared. And the area on the bottom of the can had to be the same. It's pi r squared. So our flux is just whatever that electric field is times the entire area. All okay? Any questions? All right, it's at this point where we can add all that together to get the total flux, and we get 2 pi r squared E. Any questions about what we've done here? All right. So, handled flux. On to the next part. Have handled the amount of enclosed charge. We have enclosed this much surface. I didn't draw it like this, but I think over in this picture we could probably see that the amount of surface that's enclosed is also a circle and would also have area of pi r squared. Does that make sense? The amount of enclosed charge. So when I work out the enclosed charge, that's going to be the density times either the length, area, or volume of charge enclosed. That's how we're going to find enclosed charge. Unless they're point charges, it's going to either be a length enclosed, a volume enclosed, or an area enclosed. This is an area enclosed. So I think we can just say Q enclosed equals sigma times pi r squared, since pi r squared is the amount of surface enclosed. Is that all okay? Does that make reasonable sense? So now we can begin to assemble our flux. I'm sorry, not our flux, our Gauss's law. So get back over there, Gauss's law. Q enclosed equals epsilon naught times E dot dA. This part we have found to be 2 pi r squared E. This part we have found to be sigma times pi r squared. And there we have our little epsilon naught. So we're going to assemble our Gauss's law by putting in the Q enclosed on one side and what we find for flux on the other. We have our proportionality constant, epsilon, in there. And now solve for E. Pi r squared cancels on both sides. So E becomes sigma over 2 epsilon naught. You'll notice, I hope, Z never played a role in this. Did you notice we never had to use Z ever? Because we never needed the area of the sides of the can. In fact, if you look at this expression for the electric field, this is a constant, and this is a constant. What does that tell you about the electric field near an infinite sheet? It's constant. It is uniform. The word we're going to use is uniform. The electric field near an infinite sheet is a uniform electric field. If you want to create an electric field that is constant, that is uniform in a region, you use a charged sheet. This seems to be a little has some discontinuity in our brain. Like, how could it be uniform anywhere away from it? Well, the idea is that you're never that far away from it. We assumed, even if this is a finite sheet, that we are very close to that surface. But near the surface of a sheet of charge, the electric field will be uniform. So it doesn't matter how far away you are from it, it stays the same value. It's like being close to the surface of the Earth. The gravitational field near the surface of the Earth is uniform. It has the same acceleration no matter where you are. We're saying near a large sheet of charge, the electric field is uniform. It stays the same no matter how far away from this sheet you are. There's a uniform electric field. It's nice to work with uniform fields. Working with uniform fields gives you constants that you can work in. It's easy to calculate work. It's easy to calculate energy. So when we start talking about how we're going to deal with electric fields, shaping and creating a uniform electric field is useful to us. So putting all this together in one place, kind of as a reminder, we have point charge, we have a line of charge, and sheet of charge. And again, we did this on Friday, but just a reminder, the electric field here, Q over 4 pi epsilon naught r squared, where r is your distance from the point. Line of charge, lambda over 2 pi epsilon naught z, where z is perpendicular distance from line. And sheet of charge, uniform. The three basic shapes. Just so you kind of put this in your notes, we are going to create devices that harness electrical energy and are going to use these three shapes. The one that we will probably like the most because it's the most useful is the parallel plate capacitor, and it is basically two infinite sheets. There are other kinds of capacitors that harness that energy. There are cylindrical capacitors, and they will harness or use the idea there's a line of charge. There is also spherical capacitors. Difficult to make. They're more theoretical in nature, but there are some interesting possibilities with the spherical capacitor. In all cases, you need to have a handle on what the electric field looks like around those devices. Now, put this in a long-term kind of thing. We are always trying to deal with the shape and size of an electric field. For the rest of this semester, it'll be a lot about looking at the shape and size of electric fields. These are the three basic ways that we create electric fields. It would be very valuable to commit these to memory. Very valuable to do so. if you can, shows up enough in multiple choice situations where if you have those committed to memory, you will do better than your friends. So I've strongly encouraged it. All right. To look at some other situations. And for the next, and we won't get through all of it today. We'll get through a lot, but what we really want to talk about is insulators versus conductors when it comes to charge distributions. Gauss's law works in all situations. It is a law. So no matter what the situation happens to be, you can always apply Gauss's law to it. That's going to have some interesting implications, especially as it comes to conductors. So I want to take a look at, and these are words that you have to look at closely when you're given problems. Bless you. A charged sphere doesn't tell you enough. You need to know if it's a charged conducting sphere or a charged insulating sphere in order to be able to answer real questions about it. So for the example we're about to do, let's say that we have a charged insulating sphere or insulated sphere that has charge density rho, which is total charge per volume. I mean the charge density. Now if I tell you that the sphere has radius r and total charge q, then you could probably figure out what rho must be because you know things about spheres. So we didn't get this right the first time it was asked on Thursday, but who knows what the volume of a sphere is? It is 4/3 pi r cubed. I asked for the surface area and I got that answer instead, but now we know this is the volume of a sphere. So if I tell you that we have an insulated sphere of charged q and radius r, its charge density would be q over 4/3 pi r cubed. Now, we're going to talk about a situation in which we have a uniform charge density. But there are a lot of things in nature that don't have uniform charge density. Jupiter does not have a uniform charge density. It would behave differently than this. So the electric field inside Jupiter is going to be different than what we're going to find. The sun does not have a uniform charge density. Therefore, its electric field inside the sun would not be like this. But we're going to talk about this sphere, and what I want to figure out is what is the the electric field inside and outside of the sphere. Everybody okay? Inside and outside of the sphere. Let's do outside the sphere first, because that's probably the easiest one to do. What do you think the shape of the electric field is going to be outside the sphere? I'm not sure it'll be circle. I think it's going to be radial. Right? Wouldn't it look like a point charge outside the sphere? Now, I kind of expect if we shrunk it down, get far enough away, a big sphere is just a point charge anyways, right? So I would expect that the electric field near a charged sphere would probably be radial. It would probably be coming out in a radial pattern like so. Agree? That makes sense? What kind of shape do you think would be a useful shape to use then if I wanted to find the electric field outside the charged sphere? A bigger sphere. I think that's a good idea. We'll go with a bigger sphere. And would you agree that probably the best way to do that would be to make them concentric? All right, so I've made them concentric. Now, our first job is to kind of figure out the flux. I think that I don't have to break up my integral into multiple parts since I have a uniform sphere of charge. Right? I'm just going to look at the whole thing at once. If I make them concentric, that means this distance is always the same, and my Gaussian surface would be measured by its radius, which I'll put little r. Let's not get confused. Big R is the radius of the sphere. Little r is the radius of the Gaussian surface. Can we first agree that for every single point on the surface, the area will be in the same direction as the electric field? So I can deal with the cosine right away and say it's cosine 0 degrees for every point on the surface. So I will first strip away the vector stuff and say that this is just a straight product times the cosine of 0. Is that all good? Can I go one step further and assume that the electric field is probably the same size everywhere around the surface, as long as we're concentric? So I can pull E outside of my integral. And all that's left to do now is sum up the surface of my sphere. So 4 pi r squared. That all good for you guys? So my flux will be E times 4 pi r squared. What's that? Yeah, area, right? Good. All right, so how are we feeling there? Is that all right? Well, Q enclosed. Can we kind of agree that Q enclosed is just Q, the entire sphere? All right, we have enclosed the entire sphere in our Gaussian surface. Therefore, Q. Is that okay too? So I'll have Q equals epsilon times E times 4 pi r squared, or the electric field is the same as point charge. I don't think this part was the hard part. I think that's kind of an expected result. You guys all okay with that? We get outside a big sphere of charge, it looks like a point charge. It's not the outside part that was the part that I was going to be worried about. The part that I was worried about is the inside part. But if you're outside a sphere of charge, it behaves like a point charge. Is that all good for you guys? All right. So let's do the hard part. Let's go back to my sphere of charge. And now let's talk about inside. So to do inside, you can't really see that very well. Let's go blue. I'm going to set up a Gaussian surface that is inside the sphere of charge. Right, we want to find the electric field inside our sphere of charge. So this is going to be for situations in which r is less than the radius of the sphere. We did for r greater than the radius of the sphere. Now we're going to do for r less than the radius of the sphere. So my Gaussian surface has radius little r, but my sphere has radius big R. All okay? I don't know if you'll be convinced of this or not, but do you think there's symmetry here? Like, do you think? All right. So I think it's not an unreasonable argument that the electric field inside the sphere will still be radial. Do I need to convince you of that, or are you guys okay believing that? I think it's pretty clear. Even if we just considered what's inside the blue circle, that would have to produce an electric field that's like a point charge. Wouldn't you guys kind of agree with that? The question will come down to what is happening to the outside of the sphere. So like, if I was to say that for the time being, we ignore the inside of the sphere and just talk about the outside of the sphere. Does a point, say here, have any electric field from the outside of the sphere acting on it? It's a hard argument to make. We don't have the mathematical skill, I don't think, to do it properly, meaning actually add up every single piece of charge and its effect. Because obviously there's got to be a piece of charge here that is pushing on my point in space in that direction, right? But there's also got to be a piece of charge, say, over here that's pushing this way. It's farther away, mind you. But if I divide the sphere in half, say, there's a lot more charge on this side pushing this way than there is charge on this side pushing that way. So there's a certain symmetry there. Could you just buy into the idea that with all that symmetry, probably the outer shell of charge cancels out? Does that seem reasonable? Now, it can be proven, but the math to prove it's pretty tough. So I would be unhappy to do so, but I could probably do so. So can you take it on faith that that's okay for now? Just by a nice, decent, symmetrical argument? I hope so, because that's all I got right now. And I have limited time, so I want you to believe it. It's not about belief. I mean, it could be calculated with math. So, area is this way. Electric field is this way. Can we kind of agree that the electric field and area are all in the same direction? In fact, all the same arguments should be able to be put in place to say that the the flux is going to be E times 4 pi little r squared. All right, it's going to be all the same arguments. I'm going to get the same expression for the flux. The issue we're going to have is how do we express the charge enclosed? That's going to be the issue. But I don't think that's going to be too hard, because the charge enclosed has to be the charge density times the volume enclosed. And the volume enclosed is 4/3 pi little r cubed. All good so far? I'm using the wrong symbol for charge density. Thank you for not correcting me. But we also said that the charge density is total charge divided by total volume. All good so far? 4/3 pi all cancels out. And I'm left with charge enclosed equals Q times little r cubed times big R cubed. You guys see that okay? No big deal? Well, if we could just put all that together, Q, R cubed, epsilon naught, E, 4 pi, R squared. I just want to solve for this. I'll be fast, I promise. E equals R squared cancels with 3 of those. So I have just an R over there. You guys see that okay? And I'll get Q over 4 pi epsilon naught R cubed times R. This might not look like much to you, but the electric field is linear. It builds in a linear fashion from the center to the outside edge. When R equals 0, the electric field is 0. All right. That was a lot.